Hi, my name is Ellen Gualtieri, and I am a product manager at Formulatrix. This presentation provides an overview of a cell culture automation platform that we are currently developing. 2 years ago, when we started to learn more about cell culture, we were initially surprised at how much of the work was done manually. Scientists were coming in over weekends to attend to their cells. Colleagues were trying to figure out coverage of who would take care of their cell line when they wanted to go on vacation, and stem cell differentiation protocols were quite tedious and labor-intensive. Despite all of this, there's really no great off-the-shelf solution available to automate some of the major cell workflows. As we spoke with scientists and visited labs, we were impressed with the efforts that have been undergone to put together automation by linking many different pieces of instrumentation together. More often than not, though, a large robotic arm is used to link all the pieces together, limiting scalability and layout. Furthermore, a large investment in both time from automation engineers and money is needed to get these projects off the ground. So this motivated us to look outside of the box, and we found ourselves taking inspiration from large packaging warehouses like Amazon and Alibaba, where they use robotic cars to manipulate and move goods with high throughput. We thought, why not miniaturize that concept and apply it to lab automation? And that's exactly what we've been trying to do in the past couple of years. As we work on this project, we have found that the robotic cars, which we call ROVERs, provide an automation platform that is flexible in layout. Instruments can be stacked on top of one another and accessed by rovers via elevators, as you can see here, where the blue rover is going to go up on the rover, up on the elevator, and then deliver to a subsystem. The rovers can also work in parallel. This allows the rovers to either work together as a fleet to accomplish one task or separately to accomplish many tasks simultaneously. The system is modular, reconfigurable, and expandable by only needing to tell the rover to drive to some different position. Also, it is intrinsically safe and collaborative as the rovers are small and can easily be picked up and stopped with the hand. As excited as we are to develop the rover as a general automation platform, we are first focusing on its use for automating cell culture. The system is currently being developed to support the automated feeding and splitting of up to 400 SBS-sized plates, ranging from 1 well to 384 well multi-well plates. Our goal is really to reduce the burden on support staff by creating a smart, reactive, and dynamic automation process that can self-schedule based on user input. The system will automate feeding, passaging, pooling, and plating of cells, as well as the differentiation of stem cells. It will be able to support multiple protocols running in parallel on many different cell lines, making it well suited for user facilities. We also recognize that it doesn't matter how good your hardware is. Without intuitive, flexible software, the whole product becomes useless. Formulatrix was founded as a software company, so software development and user interaction is still at the core of our engineering developments. Instead of using a generic scheduler, we are creating our software from the ground up specifically for cell culture. This creates an application-based software that focuses on the needs of the end users, providing the flexibility and options needed for cell culture work. So I'd now like to take you through the process that we are developing with this animation here. So first, let's see, you can see that an empty trough on top of this blue rover drives into the 4°C refrigerator. Media is then dispensed into the trough directly in the refrigerator, eliminating the need for long tubing. The trough is then transferred into the incubator, where it can be stored to warm prior to feeding the cells. So this means that the cells are not shocked with cold liquid. And so here you can see that the trough is then put into the storage in the incubator. In the meantime, a cell culture plate is brought over to the confluency imager. So you can see here on the red rover, it's going to drive out. Here, the plate is monitored for cell growth on a user-defined schedule. And so it's gone up to the instrument shelf and then brought over to the confluency imager that we've built. It's an inverted microscope that does high dynamic range imaging and captures images with 20 megapixel images for high resolution. It also can image the full plate in less than 2 minutes with confluent results for each well, and also report out the average confluency for the full plate. Then based on the confluency, the plate is then further processed. So say, for example, that 80% was defined as the cutoff for confluency. If the plate had reached 80% confluency, then it would be sent to be processed for splitting. If not, it would either be sent back to the incubator or to media exchanger for feed-in based on the schedule that the user defined. And so here in this example, the plate is being brought up to our 8-channel liquid handler where the rovers act as the deck. And so they move and position in the X coordinate system. And the 8 channels here are used to suspend the cells into solution after enzyme digestion and then feed it into a daughter plate based on the cell count or user-defined ratio. And so that same imager that I saw before will also be used for performance cell count with a specific cell count in plate. Then the plates are brought back to the incubator and the process continues. So this just gives an example of a simple workflow for maintaining and expanding cells, but it could also be utilized for stem cell differentiation and other protocols. So last month, in February, we were excited to show the rovers in real action at the SLAS conference. So if I can show you this, this is a video that was taken at the conference of 3 rovers that were driving around. And so you can see in this video that the rovers are driving around on barcoded mats. These mats are used to help position the rovers and they use them to navigate their environment. The rovers drive the labware into incubators, as you can see here, and then they can go and drive through and then up onto an elevator, and the elevators can go up and down, and then a spatula is labware out of the system as well as deposit it into the system. And then they can continue to drive out and drive around on the mats. So prototyping so far is really going well. We're pretty excited. We're excited to show it off and excited with the progress that's being made. Current focus is right now on the front-end vision alignment and the fleet management software. So the other subsystems are also going well, and they're well in development, and so I can show you a little bit about what we have going on there with them. And so here's a confluence imager that we built that's integrated into the system, and it's utilized to monitor cell growth, morphology, as well as perform the cell count. So full plates can be imaged in less than 2 minutes, and then that directs what happens to the plate next, either splitting or further incubation or feed-in of the plate. Also, the refrigerator is currently built and operational. There's storage for bulk media reagents and media bags, and also storage for more precious reagents in either troughs or 96 deep well blocks. Media is dispensed directly in the refrigerator, which eliminates the need for long tubing and flushing on the lines. This also makes it easy to warm media on demand. Also, the software is smart in that it will look ahead to see how many plates are needed to be fed and dispense the amount of media needed. It will also take into account expiration dates when dispensing and only make up enough media needed to support the number of plates that will be fed within that expiration date window. This hopefully will take off the burden on support staff in managing reagents and programming the system to be efficient in its usage. Our flow system, which is an 8-channel liquid handler, will be utilized for suspending cells into solution and feeding them into daughter plates. The smart technology built into it for liquid class and height detection make it easy to integrate into the automation process with limited calibration and labware definition needed. Also, it will be used for pre-mixing media and solutions on demand as needed. So as mentioned earlier, software is just as important as hardware in this product. A great deal of resources are being put into the schedule and software, which is being designed to be reactive and dynamic. We are currently working on different designs for the user interface in design and protocols. So here's an example of a flow-based diagram where predefined processes are available in a toolbox to then drag and drop into a workflow with options available to define. So this is an example where you start with imaging, where you can, on a predefined schedule, and you can define those parameters here. And then if it's greater than 80% confluency detected, then you would split the cells with the options for defining the type of enzyme and incubation period. But if it was less than 80% confluency, then you would feed the cells based on the schedule with the defined media types. The goal of this whole design is to be simple enough for lab scientists to utilize it and not require automation engineers to script protocols. Of course, if you love scripting, we will make that available for you. So this really summarizes what I wanted to review today. I am Ellen Gualtieri. I'm the product manager of the system and happy to answer any questions you may have. Feel free to email me or call me at these numbers here or reach out to your regional sales representative. And thank you for listening, and I hope you have a great day.